Well, hello everyone, and welcome back to Adrian's Digital Basement 2 Super Mini Mail Call, and this package comes from Gavin in Tennessee. So hi to all my Tennessee viewers. It's a big box, so I'm just opening up, pulling everything out of it, and on the top was this piece of cardboard that looks like it's been run through some type of a die cutter that turned what was a cardboard box for a regular Canon printer into packing material. That's kind of freaking awesome, I gotta say. And inside the box, we have two more boxes, a couple floppy disks, some cables, a bunch of folders with documentation. I don't know where to start. Looking at the documentation here, this one has some manuals and it says Epic Instruments Incorporated WaveDisplay. Seems to be talking about something called the ADC-1 from 1985. At least that's the date code on this set of documentation. Yes, and here we go. ADC-1 Owner's Manual, Remote Measurement Systems Incorporated. And it actually says June 1983 on this manual. All right, inside first box, we have a device of some kind wrapped up. And inside the second box, we have a bunch of miscellaneous parts, with this thing here being the actual device in question. We'll take a closer look at that in just a moment. Let's get this all unpacked. All right, so I'm just unwrapping things randomly. This is the Wavesaver 10 from Epic Instruments. Trigger level, AC/DC. This almost seems a little bit like an oscilloscope. What's on the back? Does it have any ports? This has an output, trigger, external clock, digital port, scope, and plotter. So that's quite the curious device. I can't really tell what that is. Going back to this ADC-1, a whole bunch of digital inputs, analog inputs, controlled outputs, remote measurement systems from Seattle, Washington. A couple different dip switches on here, including baud rate. I just unwrapped this little box, the BSR X10 controller system. So X10, which I don't know if it's even related to these at all. X10 is a home automation system from the, I think, late 70s. It was actually popular into the 2000s. I had a full X10 setup at home before we had Zigbee, Z-Wave, and all the other home automation stuff we have nowadays with controllable lights and whatnot. The way this worked is you had these little modules. You'd say plug a lamp into a little module, plug that into your wall. It communicated over your power lines. You had channel selectors, so you could select a different channel, device numbers, and then say with a remote control, or something like this, ultrasonic command module. I bet you this has a remote that goes with it. In fact, it's probably this right here. So it's an ultrasonic remote. You probably will use that remote to talk to this box, and then it would talk over the power line to the modules for your lamps and different devices, allowed you to turn them on and off. The later systems, like the one I had wireless remote controls, and there was a little receiver box that you plugged into the wall and used RF, and you would communicate from the remote, you had multiple remotes, to that receiver module, and then it would talk over the power line to your various devices, light switches and modules. But the fact is, I just opened this up, and yes, this is an ultrasonic remote control. So it uses ultrasonic tones. It's like a tone generator when you push these buttons. Oh, it's actually electronic because it has a battery on here. So you push the different buttons, it would send ultrasonic tones out, picked up by this box, and then it would transmit to your devices in your house. The whole system was kind of slow, but it was reliable. And I remember the X10 system I had worked really, really well. Kind of the downfall of it was LED light bulbs and compact fluorescent before that. It worked really well for turning off lamps if you had incandescent bulbs, because you could dim them and whatnot. There were lamp or appliance modules, they were called. So this was a module you plugged in the wall and had a relay inside. You could obviously plug compact fluorescent or LED into that, it'd be fine. But if you had a wall light switch, you know, where you would turn lights on for an entire room and you had overhead lights, if you put LEDs and compact fluorescent there, that generally didn't work well, because the module you had installed in the wall where you replaced the on-off switch actually was powered by like a parasitic power through the incandescent bulbs. So it would actually run them at a very low power level. And even though the light itself wouldn't turn on, it was acting like a resistor, and that would power the light switch. If you put an LED in there, it stopped working. So that's kind of when I took it all out, and I've since switched to the more modern stuff. So we have a couple AC adapters. This one, 18 volts AC. Ooh, this one is Radio Shack Archer branded. Love it. Look how old school this looks. Wow, 9 volts DC. Not sure you can really trust these anymore, because this will just have a simple bridge rectifier inside, or half wave rectifier, and a capacitor to smooth it out. And the capacitor is probably dried out, which means this will just output kind of a half AC waveform. It looks like we have another X10 piece of hardware here, and this is another controller. So it's actually very similar to the one with the remote control. This is just a wired version. So you would plug this into your wall, have this next to your couch, for instance, or bed, because this, well, no, this seems to have like bedroom, family room, and these were actually 2 positions, so on and off. And these are device numbers. So this supports up to 8 devices, and you can just turn things off and on with this. And of course it's yellowed, but you might have these around the house. And yep, there we go. X10. Oh, this is actually the RS-232 interface as well. So yes, it does have a serial port connection, I assume. And this is, yep, for a 9-volt battery. I think the way this worked is you would program this with RS-232 from a piece of software on your PC, probably like a DOS thing. And this would have most likely some scheduling or something inside here. Maybe it had a clock capability and to keep time based on the AC waveform off the line. And then you could have it turn lights off and on in your house, do stuff like that. Home control interface. And we have some floppies here. So this is probably for this PC XT and IBM compatibles. Version 1.01. I have to think all of this stuff has been archived, but in case it hasn't been, I'll try to recover the data off of these. That looks okay, that disk, and I will upload them to archive.org. So we have a few X10 disks. These all seem the same. Or no, the version's slightly different. 101 and 1.0 and 1.0. And here's a CPM disk, and this appears to be probably for the ADC-1. And it looks like we have another one, a backup disk, with a printout of the files that were on it. Oh, we have the manual for the control interface with the programming guide. So it looks like the main functions of the interface are real-time clock, stores timed event relating to control of lights, appliances in the home, and stores graphic data required for the computer to display the details of lamps, appliances, entered into the house by the user. Transmit the X10 control signals over existing house wiring to control the lights and appliances to the modules. And again, you would be plugged in with a serial cable from this to your computer, and then it would be transmitting over the main line cord there. Wow, this actually goes into, well, the pinout of the serial connector, even the protocol that's being used. Download base house code and stuff like that. ACK messages, upload, set clock. Wow, this really tells you how to do everything. Back when I had X10, I never had one of these. I had like a module that you could use with Windows 95, but I didn't really ever use it. I just didn't rely on any automation. It was just really for turning lights off and on without having to get up and go to the lamp on the other side of the room. These were pretty ubiquitous and popular from my recollection. And since this had a little bit of memory in there using the stuff that's in here, you could program this, and then even when your computer was turned off or being used for other things, this would still do all those home automation type functions. And what's really cool is that since this was all documented, you could hook this up to any 8-bit or 16-bit or whatever home computer and potentially write your own software to program this thing to get the full functionality of it. We also have the computer interface owner's manual, so as opposed to the programming manual, which we were just looking at. And there it is, the System X10. So mini controllers, telephone replicator? I don't even know what some of this stuff is. By the time I was using it, a bunch of this older stuff was sort of deprecated. So these were those wall switches I was talking about with incandescent bulbs. These were the lamp modules you plugged in the wall, and then the appliance module had a relay for turning things on and off like your television set. I assume the telephone responder, I said replicator, the responder is so you could call into your house and check the status or maybe control things remotely. And it kind of tells you here how to set stuff up, how to set up the lamps, set your house codes and unit codes, and you know, it is all pretty easy. Oh, there it is. There's installing one of these wall switches. So these didn't use a neutral connection. As I said, it would actually just use a parasitic load through the lamp and everything to get the power to run this. Obviously, it was quite low power. And I recall you could push this button to like turn it off and on. Those two things there are the use a screwdriver to adjust the house code and the unit code. And I think the switch on the bottom was like a lockout. If you wanted to keep the light off permanently, you could do that. And I vaguely recall you could press to turn off, press to turn on. It was a momentary switch, and you could hold it and dim as well. Oh, look, and here's some of the different components. So there's that telephone responder. It had a little thing, a little remote. So you would hold it up to the phone, push buttons, and it would make tones to turn stuff off. Oh, that's hilarious. Control the central heating even. The mini commander, so it's just a small remote for next to your bed or couch or whatever. This was a timer module, so it was like an alarm clock in a way. keep it next to your bed, for instance, but it could also turn lights off and on. The burglar alarm interface, curious. Lamp module, wall receptacle module, so that was an entire wall receptacle, 3-prong, appliance module, 2-prong. Here are the different light switches. Yes, there was even a remote switch for 3-way capabilities, heavy-duty appliance modules, thermostat controller. I vaguely recall what this was. I think what this would do is it would heat up under your thermostat, so you would attach it just below it. So see how it says turn down central heating or air conditioning when you're sleeping or not at home. And this would allow it to trick your system into running at a different temperature. So it would slowly emit a little bit of heat. And then that would make your heating think it was warmer in your house than it actually was. Never had one of those myself, but that's what I vaguely recall that working like. And yeah, look, don't use a wall switch model to control a fluorescent light fan or any other kind of appliance. This can cause damage to the module and or the light/appliance. All right, anyways, moving on, we have a bunch of stickers for different stuff. I thought this was a radiation symbol for a second, but it's just a fan. Air conditioning, you'd obviously have to use an appliance module. Coffee maker, record player, stereo, lamps and things, kitchen fan. It's all pretty hilarious how old everything looks, all these little icons. Love it. Are these actually sticky still? Yeah, there's actually a little bit of stick left on them. That's cool. The CP290 Home Control Interface Advanced Programmer Guide. Look at that IBM PC. So again, that's for this thing, but I guess just more advanced for the programming. Actually, no, this looks exactly the same as the one we've already looked at. And I think this is the manual for the ultrasonic remote control from BSR. Yeah, look at that. Awesome. So the system was somewhat open. I mean, I'm sure it was all licensed, but other manufacturers made stuff for this. For a long time, x10.com was a place you could buy stuff for once the internet became a thing. But these third parties were making things for X10 and it was all interoperable. I guess as long as it had like, you know, System X10 on there, then you knew that it was going to work with it. And yep, this is definitely, that's definitely the manual for the ultrasonic controller. And incidentally, you could have groups of lights as well on the same code, so you could control them all together at the same time. It was very flexible, the whole system. Looks like we have a manual for the actual software, so we can actually take a look at what that looks like. So days of the week, specific days, files, times, changing the house code, installing the modules. I mean, you know, if you do any home automation, this is pretty much that, but it didn't have any sensor. So it didn't have like if then, so you couldn't say like, if someone walked by a motion sensor, then do this. I don't think it had sensors at least not at the time this was released, like in the 80s. I don't think it had sensors, but you can have a printed log if you so desire. And yeah, okay. Pretty self-explanatory to be honest. Looks like we have the same manual multiple different times, even though there's only one of these modules. Now, I did just notice that this cable was included. So this is obviously the serial cable for this box. That's cool. And yep, that would plug into a PC. That's the correct gender for 9-pin serial. All right, moving on to the other stuff. Here's something, a little letter that was included, but I don't think this came from Gavin. I hope you find these devices interesting. The Remote Measurement ADC is an early example of a versatile and affordable interface that allows you to communicate with a number of different sensors and to control X10 devices. I wrote a library of routines in Fortran to facilitate its programming and taught a course to expose students of how computers might be used in collecting experimental data and controlling devices. Good luck with your exploration of these early efforts and in bringing computer automation to a larger audience. This letter was addressed to Gavin, and it looks like Larry didn't necessarily design the interfaces, but he did write libraries in Fortran to control it. So what's really curious is like, how would this actually control X10 devices? I mean, maybe it's in the manuals, because the only other cable that came with this is this thing here, and it has Epic written on there, and then some other D-sub connectors, but I don't see how to interface this to, say, the power line switched stuff. Lots of analog inputs, digital inputs, and then we have controlled outputs. So it goes without saying that a box like this plugged into a PC and has a D-sub there, just a single 25 pin. And you know what? I don't even see how this thing gets powered. It must be powered over the D-sub, I suppose. Something like this would allow you to have lots of digital I/O switches and relays and things like that. So I can see how home automation work with this. Again, I don't quite see how this works with X10. There were a couple more discs, by the way. Epic Industries WaveDisplay. and Epic Industries Ming. Okay, those two discs were in the box as well. Let's check out the manuals here, see if we can figure out what's going on exactly. Everything that you see here, by the way, if it's not already scanned on archive.org, then I will have it uploaded there. It might not be in time for this video going live because a friend of mine does my scanning for me, but it will get archived at some point in the future. All right, so the ADC-1 is from 1983. The remote measurement ADC-1 is a low-cost, reliable, and easy-to-operate data acquisition and control system. The ADC-1 provides computer with the capability of sensing and reacting to information gathered from the surrounding environment. The ADC-1 functions by measuring the sensor's analog voltage output and converting this to digital number, which can be evaluated by the computer. Under conditions which can be programmed to any computer language, ADC-1 can be employed to control external devices. You do not need to have sophisticated electronic skills since the ADC-1 supplies the computer sensor control interface. And with the ADC-1, you are free to concentrate on the design and installation of your sensors required by a specific application. 16 analog input channels, 12-bit ADC, 4 digital inputs can be used to monitor or count on-off signals, and 6 controlled TTL outputs allow operation of external control devices. Remote control of applications and lamps via signals transmitted over AC wiring to BSR modules. Well, that's X10 right there. That's what that's talking about. Optional instrumentation amplifier providing RS-232 communications for easy interconnection to most hosts and modems. Oh, I just realized something. He's talking about a smaller box. I forgot to show this. Yes, this also was included. This is obviously the power supply. So this plugs into your power receptacle, AC line carrier transmitter. So this is obviously how it transmits to X10. Then this would plug into the side of the unit, and I assume this is the DC input to actually power the unit. And then here's our serial port pass-through. And this particular power supply that was included, the Archer one, has the appropriate TRS jack to connect to that. I don't know if the other one is also the same. No, this one is just a normal, this one is the AC one. I don't think that is related. All right, so that's required, obviously, to get this thing powered up. And then, of course, communicating to your computer to use with those libraries that was mentioned in this letter that Larry wrote. The smaller box, which plugs into the alternating current outlet, is the transmitter for modulating on the AC wiring which control the remotely controlled outlets. The transmitter was placed in a separate enclosure to isolate AC voltages from the sensitive analog to digital circuitry. A small flat 3 wires runs from the transmitter to the DB25 male with pins. This connector mates with the female DB25 on the right-hand side of the panel AD1 and will serve as the AD1 end of the cable for your computer. Communication with the AD1 require wires connected to your RS-232 of your computer and the DB25 on your ADC-1. Talking about the power supply, it says there's no internal power supply at all, and the power source should be capable of supplying 20 milliamps at 5 volts or 35 milliamps from 6 to 24 volts. This power can generally be obtained from the computer or modem connected to the ADC-1. Most computer power supplies are designed to supply more than 1 amp, so the addition of 20 milliamps should not cause overloading. Yes, that is for sure. So that kind of makes me wonder, well, how can it be 6 to 24 volts or 5 volts? So is this really what should be powering up as opposed to just 5 volts? All right, it says pin 18 on the ADC-1 is for 5 volts, regulated or current limited 12 volts. Pin 9 should be used for supply voltages exceeding 6 volts but less than 25 volts. So there must be a 7805 inside the ADC-1. And it says if you want to check to make sure everything is working, you can check the 5 volts terminal. Looks like we have 5 volts output right there on those terminals. So now it's going into how to use this thing, and it's giving some examples of Microsoft Basic commands. It's basically telling you, this is assuming you're using a computer that has a serial port that you can just write to directly with peaks or in or out commands, which I think was kind of common on CPM-based systems like Altairs and IMSI and stuff like that. So yeah, we have some basic examples. So you write out to the port number 24, which is some kind of a command, I think, 160, and you take that in, do some basic stuff. Tells you how to read the digital inputs, testing control of AC line carrier modules. So yep, it's telling you how to control the X10 here, which of course, I can't really test this because I don't have any of the lamp modules or appliance modules anymore. But this should allow you to actually control that stuff very similar to what this thing does. But this is doing it in a way where you can write basic programs, and of course you have access to all these sensor inputs, so you can trigger off of the sensor inputs, and that's not something you can do with this little box. Programming the analog to digital converter to read the onboard temperature sensor. Bunch of stuff on how to program, like example programs on controlling the X10 stuff. Wow, this is neat. Now the manual is getting into all the technical details on like thermocouples, solid state sensors, wind speed sensors. This is very cool. I would have had so much fun with this. Optical encoders, security system sensors, floor mat pressure sensors, ultrasonic sensors. This is pretty cool. Home automation is like something that's very easy to get into. Now you get a little home automation hub. Everything's connected with Z-Wave or Zigbee and other, I don't know, more modern stuff, Matter and stuff like that. And you can have motion sensors. And I have some in the basement here. There's a little one up there actually, and it's really for controlling the lights. So yeah, the lights and stuff is all kind of automated here. And I can turn on these lights back there. There we go. Those ones, those are controlled through my home automation system. And I have a stream deck with some buttons on it. Whoops, I missed pushing. Oh, there we go. That button switched. Took a second for that to work. And I use a home automation hub at home, but there's all sorts of open source alternatives, like was it Home Assistant, I think is the big one that people use. But this was clearly the precursor to that. And you know, you had to really know about electronics, how to hook up wired sensors. So if you stepped on a floor mat, it would then kick off a whole series of events, which you could then turn on lights, appliances, you know, even send you a, I was gonna say email. Or SMS. No, it wasn't doing those, but you can at least log that stuff. And it's pretty fascinating to see like the really early precursors of all of this. And look, here it is talking about interfacing the ADC-1 to your VIC-20 or Commodore 64, Atari, S100 based systems like the Altair and IMSI, North Star Horizon, Osborne 1, Osborne Executive. I assume because this is 83, it's going to have the IBM PC in here as well. Yeah, the Epson HX20, but here it is, the IBM PC. And then, yep, more basic programs for specific computers. So it looks like for the 64, it's using SIO. So it's obviously using like a little serial box of some kind that you would be plugging into this thing. The Atari computers are capable of communicating with the ADC-1 via peek and poke commands. Clock channel 3 with 1.79 megahertz and set the baud rate. Right. On the other hand, if you're using an IBM PC, you're actually having to open one of your COM ports, and that's the command. You can do this in BASIC. So I think print statements and input statements to #1 is going to basically communicate over that COM port. And we have examples of doing this with graphics as well. If you're going to write something kind of fancy, let's look at this. Look at these examples. This is amazing. And then here is the entire instruction set for the ADC with all the bits and stuff. And wow, we have the data sheets that make up this thing. Intersil 12-bit binary AD converter and a couple of the other ICs that are inside of this thing. How cool. Oh, so it does have an onboard temperature sensor. I think it said that earlier on, so it must be internal to that. Something made by Analog Devices, the AD590. Yeah, we even have current probes. So cool. So much of this is so trivial to do now with microcontrollers. Even in the last like 15 years, using something like an Arduino, you can do all this like AD stuff. Obviously communicating with X10, not as easy, but you can interface an Arduino super trivially to Home Assistant running on a Raspberry Pi, which also has a bunch of GPIO lines itself. So much of this is something you can do so easily now for just like pennies on the dollar. Something like this was probably relatively expensive. I mean, it was still affordable, I'm sure, but it wasn't cheap like all this Arduino stuff is now. So it just shows how far we've come since the 80s in this whole home automation world. Why don't we open this thing up and take a look inside? Because I'm sure there's never been anyone who's actually shown one of these off on the internet. Let's see the correct way to open this. I kind of have to assume when we open this thing up, there's going to be some kind of a microcontroller or CPU with a ROM, a little bit of RAM, because if this thing has a command structure, which it does, it's going to need at least a microcontroller for that to happen. It might just be like an Intel 8051. That would make sense. It has a tiny amount of RAM, just enough for commands and things like this, and then some ICs that interface those to all of those GPIO lines. Okay, we have a couple of those Intersil ICs. I think that was the one mentioned in the data sheet. These are the AD converters, I think, for all those analog inputs that we have. And what I don't see on here is any kind of CPU and microcontroller with RAM. I kind of have to imagine that these Intersil chips have a little bit of smarts in them and have a way to issue commands to them. It's the only thing I can really think of, since we don't see any ROMs or RAMs on here. I mean, I have a bunch of stuff here that I just don't really recognize. I mean, these are CMOS chips, I guess. Yeah, 4017, 4174, that is. 1982 date code. And yeah, that's inside this thing. These are all the connections to all of those terminal strips on the top side. And I'll just give it a slow pan. If you recognize anything that looks interesting, yep, shout. Made in USA. That's the serial connector there. Remote Management Systems, copyright 1983, ADC-1. All right, that's the other side. We got some bodges. Not a lot going on, but just the bodges. All right, there we go. It's all back together. Now, one thing that's interesting about this product is I think that these computer interfaces, this thing, came out later. Like we saw date codes on here of like 1986. No, it doesn't really say on here, but I think I saw looking in here 1986. And we know this is from 1983. And this obviously is more capable because you have all these sensor inputs, while this can't hold programs to run while your computer is busy doing other things. Obviously, with an attached computer, and you could use even something like a VIC-20, or really anything that's even inexpensive, you could really do a lot more with this based on sensor values, if-then statements. It's just not something you could easily do with this. And I think that's really the allure of something like this, and I think this might be one of the first things available for X10 to bring home automation to the X10. This thing is probably one of the earliest examples from 1983 of home automation that there is. That's freaking awesome, to be honest. Let's open this box. I'm going to use my NewTek screwdriver because the screws are quite recessed. Let's see what it takes to interface something digitally to your power lines. It's probably going to be sketchy what we see in here. I kind of recall that there was a lot of sketch going on with all of the X10 stuff. I don't think we're going to find an optocoupler in here. I think that's a little too new for this time period. So this is probably, I'm going to hope it's coupled with a transformer of some kind for some amount of safety. Oh, are those optocouplers actually? I think those are. We have some serious heat there from that little diode. I assume it's a Zener probably. This here is just a regular 555 timer. But what is this stuff? Connecting your digital interface to the line voltage. Potential death if you aren't careful. Yeah, these are optocouplers. So that's the 4N33 that we have two of in here. Okay, well, that's a little bit less sketchy than I was thinking. So I don't know really enough about what it takes to actually, you know, send that signal or whatever that's going for X10, but it's obviously, you can see there's not a lot going on here. This is a single-sided PCB, so you don't need a whole lot to communicate with X10. It's relatively low frequency, if I recall, like in the kilohertz range. And it's definitely transmitting though, so it's kind of like an RF thing. But yeah, that diode is seen better days. So obviously it's pushed a little bit hard. So it goes without saying that you can tell by the hook and loop, aka Velcro, that this was designed to just stick like that. You would plug that into the wall, and then this whole little harness thing would connect up to the side of this device. And we have a little bit of a pinout going on there. And then this would inject the power into this box to power it up. This is probably powered off of the 120 volts mains. Actually, you know what I didn't look at when I had this open is I don't, you know, this is, we saw in the manual this thing can accept either 5 volts input, regulated 5 volts from an attached computer, or you could use a power supply like this. And I just am curious, this may not be actually what this accepts. And before powering this thing up, and I think it's not a good idea just to randomly power this up, because what if this is not what this is expecting? What if this wants just regular 5 volts DC? So I probably need to refer back to the manual before I power this up and check to see if the pins that this is connected to, this TRS jack is connected to, is the regulated or the unregulated input. Now we do have a bunch of other documentation here, and these might be about the libraries that were talked about from Larry. Yep, these are definitely those libraries. Did it say it was Fortran? Yeah, Fortran, which is a language I know basically nothing about. Never written anything in Fortran. This is all stuff to absolutely be scanned and archived. Wow, here we go, version history. 0.06, 1984, and all the way up to 2.06, subroutine. Yep, neat. So my assumption is what we see here, this is just a printout of what's on those floppies. So I'm going to try to archive those disks. And this will obviously be scanned and saved on archive.org as well. All right, and in the next folder, we have a little bit of addendum. It looks like how to use the brightness commands for the ADC-1. So this is X10 brightness command. So dimming and well, we're dimming and brightening the lights that you have plugged into the lamp modules. BSR codes are transmitted on the AC power line within 100 nanoseconds of the zero crossing of the AC voltage. Each code takes about 22 AC cycles to transmit. The ADC-1 normally waits a few extra cycles before charging the BSR busy done bit, which is checked in lines 70-20 to 70-40. We were recently informed that if successive dim or brighten commands are sent within 3 AC cycles after the preceding one has been transmitted, then a rapid change will occur. However, the ADC-1 is wired to prevent such rapid sequences of code transmissions. The following hardware modifications must be done to permit the rapid changes. Yeah, rapid retransmission. Oh, that's cool if you want to dim or brighten your bulb very quickly. And we have a little bit of schematics here. Oh, I didn't even realize that one of those intersil chips was actually the UART. And then we have the ADC. Actually, you know what? This looks like the entire schematics for the entire box. That's what I'm thinking this is. And our next folder, oh, promotional material. Oh, cool. Wow, this is awesome. Here's what the ADC-1 in your computer can do for you. Enable you to collect analog data from environments, variable conditions such as temperature, energy consumption, light intensity. The signals can be converted to digital values by a 12-bit ADC. It can let your computer evaluate the data and react by directing the ADC-1 to control external devices. There is the ADC-1 with this little attached box. Take control with the ADC-1. Remote management system is sophisticated, easy to operate data acquisition and control system. Examples, siren, lamp, heater, air pumps, obviously with a relay because it's just TTL outputs. Inputs, security, lights, energy, moisture, temperature, basic, Fortran, Forth, Pascal, assembly language, yep. Oh, price list. Oh yeah. So the ADC-1, $329, 1983 prices. Remember, I'll put a conversion on screen now. With instrumentation amp, includes tabletop enclosure, AC signal transmitter, and manual. Okay, so this is with the little box for controlling the X10 stuff. That was just an extra 40 bucks. Manual, $8 if ordered separately. Software diskette listing in manual, $15. So you don't really need that. You just have to type it in manually. Temperature sensors, right. Okay, analog devices, 590JH, $7. Wind speed sensor, anemometer, $45. Light levels, photovoltaic cells, $6. Electrical energy consumption and probe. Okay, so that's a current clamp, AC current clamp. So you can measure, with $75, you can measure how much power something's using. You can take action on that, which is actually something that I do. I have an old dryer from the 90s, but I have a current probe on it hooked up to an Arduino with a whole temperature or a power sensing thing. And I get notifications via complex setup of things in the back end. I get a message on my phone when my dryer is done, which is great because if I'm away from the dryer, it used to have a buzzer that I disabled because I hated that noise it made, but I can be totally away from home even and know when my dryer is done. I also have some other stuff going on with those different current probes, measuring the house current usage. I'm pointing the power meters, or power panel is over there. So I kind of know what's going on in my house at all times based on that current probe. Wall switches and appliance modules, all 20 bucks, and 220 volt appliance. Yeah, if you had like a dryer or something that was 220 volts or 240 volts nowadays, that's what it would be. Yep, this higher cost module could control that. Shipping $5, and you can pay with your Visa MasterCharge. Remote measurement systems in Seattle, Washington. Actually, it looks like we have a different price list that is from potentially later, 1984. Price is the same though, so it hasn't really changed. Yeah, it looks like everything is basically the same price. Relative humidity sensor, that's new. I didn't see that in the other one. Calibrated, $100. Cables, sensors, control modules. These are the X10 modules again. Push button, looks like it's gone up $2 actually from the other one. Software diskettes, including for the Macintosh. 1984, so we're talking really early there for the Mac. 64 Osborne, all the stuff that was listed in there. CPM 8-inch disc, K-Pro. Thing that's really funny about this is you would need to keep your computer running 24 hours a day just to run this thing. So this box, which was almost $400, would then require you to have a computer That was an expensive proposition, although by 1984, you could buy something like a Commodore 64 for, I think, $200. So you could dedicate your 64 for $200 with this box to home automation. So if you were really serious and you were okay spending a substantial amount of money, you could totally run home automation. Yet you have a dedicated computer just to do that. Okay, so Larry worked at the Department of Chemistry at Bates College in Maine. So it looks like Dr. Shore here was teaching a course, a university level course, on home automation and sensors and automation. How cool is that? And here's an updated letter talking about the systems that are supported now. Apple II, Macintosh. They were very sure, making sure whatever computer you had, including your portable 100 from TRS-80 or your color computer, TI-99, Victor 9000. Oh, that's so cool that all these things were really supported. So these guys were very serious in supporting all of the different systems, making sure that if you had any one of these, you could do home automation with it. And now we have, I think this is documentation for the WaveDisplay, which is that other piece of equipment that we have here. All right, let's take a look at what this is, because I'm really curious about this. So the Wavesaver 1, what is this exactly? This is a Wavesaver 10. Wavesaver 10, 8-bit, 10 megahertz real-time sampling, 4K by 8-bit memory, pre-post triggers, digital output interfaces. Is this like a logic analyzer from 1984? And WaveDisplay software, $100 for your IBM PC, used with Wavesavers or any data acquisition system. Although it's talking about 10-to-1 probe, so it's almost like an oscilloscope as well. Well, luckily, it's all documented here, so we can read through this. So the Wavesaver is a digital recorder capable of storing transient analog signals and waveforms for display on any oscilloscope. Imagine being able to capture any signal occurring before and after the trigger point with precise flicker-free recordings down to DC, with the auto arm function of the Wavesaver can record signals in a semi-real-time mode. With the Wavesaver, you can extend or expand the capabilities of any oscilloscope. As a touch of a button, the Wavesaver will record and display complex waveforms and transients with a resolution of 1024 bits horizontally and 8 bits vertically, 1K times 8. The Wavesaver is not just for oscilloscopes either. Its output is chart recorder compatible, effectively increasing the response of the chart recorder to 500 kilohertz per point. The digital output interface lets you extract digital data in digital form. And if we recall, there was a floppy disk here. I think there was another one as well. Is it this one here? Yep, this is it as well. So we have 2 pieces of software for it, or at least 2 versions of it. And there is a cable that came with it, and this says Epic data transfer on it, and this device says Epic on it. So Epic control plus flash trigger, 25 pin plus a TRS type jack, large connector. I don't know what that would plug into exactly. And then this obviously plugs into the back of the device itself. I kind of recall that this has, yes, this has what looks like a 15-pin connector on the back. Kind of makes me think that the PC that this went with, that this software was running on, had a special card, a data acquisition card, that allowed it to, well, sample that data. Those pins are a little bent up, but nothing we couldn't fix. But I don't have the original card. The applications are endless in biomedical, industrial, general lab work, countless other fields. The Wavesaver would ease and simplify problems in waveform analysis. So this company was based out of Foster City, California. And on the back here, we have a little bit of specifications. Now, I'm pretty sure the one we have here is the 10H, which has 4K by 8 memory versus the Model 1, which looks like the spec sheet is for that one. $1,295 in 1984. Not cheap, but you know, not as expensive as I would have thought, to be honest. But yeah, this looks like it's for that Model 1 with 1K of RAM, or whatever storage, I guess you can call it. Starts recording after detecting a trigger, stops recording after detecting a trigger. So I think it just records whatever, a certain amount of data, I suppose. What this looks like it's talking about doing is it converts your analog scope into a digital storage scope. So you could do single shots and capture waveforms. And what this must do is just play back the waveform over and over again to your oscilloscope, which lets you stop and look at a waveform. How freaking cool is that? I mean, nowadays we have stuff even as crappy and cheap as this little multimeter, which is also a digital storage oscilloscope, a 2-channel one, which is far, far more capable than this device ever was. But in the 80s, you know, these things were beyond people's wildest imagination. I don't really know much about the history of oscilloscopes or digital storage scopes and when the first ones actually came out. I know Tektronix and HP Agilent, whatever they were called at the time, had big CRT-based scopes that were digital storage scopes. So it had a computer, and even though it used a CRT, it was still, you were looking at a digital waveform with a bitmap graphics, and it had all the capabilities of capturing and displaying waveforms like we do with all our modern scopes. But that was pretty revolutionary at the time and extremely expensive. So it's fascinating to know that something as simple, well, I don't know how simple, but something as inexpensive, relatively inexpensive as this, could give you this ability with your regular analog scope. Now back on the price list, we have the WaveDisplay software packages, which my assumption is that's what this is here. So this is for the PC. It only required 64K on the PC. Wow, I don't think I've ever seen software that was literally designed for the base minimum configuration of the IBM PC. Because the earliest version of the 5150 had a maximum of 64K on the motherboard and a minimum of 16K. Can you imagine trying to run MS-DOS on 16 kilobytes of RAM, or even 64K for that matter? But then very quickly after that, the second revision of the motherboard had a minimum of 64K, maximum of 256K. That's just on the motherboard. You can still plug ISA cards in to expand the memory up to close to the 640K. I think the original 5150, the revision A version, which I have one, has a max supported memory through the BIOS of like 576K or something less than 640. I don't remember the exact specifics. But the later version, the 256K motherboard, that could go all the way up to 640K. Now it looks like there was another little device you could probably get and it plugged into this that would then convert the parallel data to RS-232. I'm pretty sure self-contained IBM PC compatible. I don't think that's just this cable. I'm imagining that this large connector here was plugged into a data acquisition card that wasn't made by this company. And I don't see listed on here any of their, like any other data acquisition cards that you might use with this thing. Okay, so we have two manuals. Looks like this is for the software and this is for the instrument itself. Let's just see what the front cover looks like. There it is. Wavesaver Transient Waveform Recorder. Oh, Dr. Larry Shore was one of the owners of this product, I guess. So this was also used at that university in his classes and whatnot. So vertical resolution was 8 bits, which actually is not that different than a lot of the cheap scopes. I'm sure that's exactly what this thing uses, an 8-bit DAC on it. Max digitizing rate is 10 megahertz though, so that's relatively low. I don't really know what this actually is, but this is probably more like 50 megahertz usable or 40 megahertz usable. Static RAM, we have 4K of static RAM. That would have been very expensive at that time. And of course, back in the day, there was no FPGAs to help this work. I don't even know. We'll have to open this up to look at what it's doing inside, maybe, or it has maybe schematics inside. So yeah, you have an ARM signal, triggers to get it to capture the data. Vertical output from 0 to 8 volts. Mid-scale, so a value of 127 because it is just 8 bits, is 4 volts. The Waveform 10 is basically an oscilloscope add-on, which will give digital storage capabilities to any oscilloscope, effectively transforming a regular oscilloscope into a high-speed digital storage scope. Maybe they had these in 1984, with the added features of being able to interface and transfer its captured data to most personal and lab computers. Being a digital instrument, the Wavesaver 10 does have some differences compared to a regular analog storage scope. Yes, by the way, analog storage scope, that was something that, I mean, at least Tektronix had, but probably others as well. So it actually used a digital storage tube. The actual tube itself was able to store the waveform. So you could capture something and it would maintain what was sort of drawn on screen. Like the phosphor itself had kind of infinite persistence, and it had to do with plates and charge levels and voltages and stuff like that. Pretty advanced stuff, but that's something that Tektronix kind of developed back in the 70s, I think. Maybe even before, but at least commercialized it in the 70s, I think. And you know, even in the 80s, that was a thing that people had to use because digital storage, using a buffer, a frame buffer that is, and you know, digital bitmap display, that didn't really come until later, until computers had a lot more processing power to be able to have high-speed capture of data and then display the output through a buffer and all that kind of stuff. That was expensive and complicated. So I think analog storage scopes was really the way of how this stuff worked, at least at a level that any sort of normal person, like in a lab, which was still expensive, could afford. And yeah, so it says right here, the main difference to an analog oscilloscope is it holds the waveform by burning in the trace into the CRT itself, while the Wavesaver holds the recorded data in its digital memory, thus adding the flexibility of being able to extract the information recorded and thereby allowing a more precise examination of the captured data. The Wavesaver 10 converts defined sample points of an analog waveform and converts them to points in the digital equivalent codes. And these codes are then stored in the internal memory. After memory is filled, the codes are then recovered back into their analog equivalents. So this is like an output to your scope, I guess, and then is continuously played back on the oscilloscope. That's kind of what I thought was happening. Thus, transforming a regular oscilloscope into a storage scope, but with none of the undesirable features such as blooming and fading effect that is inherent with most analog type storage scopes. So the recommended setup is 1 millisecond with 2 volts per division. So that's right, 10 volts, I guess they're saying. But remember, the active space or whatever this thing can display is 8 volts peak to peak. So there's definitely some limitations for this thing to be able to capture and display the data. When you're using the scope of the Wavesaver 10, it's really being used as a display. So it's not really functioning as a oscilloscope anymore. It's just sort of displaying the memory of the Wavesaver, which I'm kind of thinking whatever you're capturing, like before you actually capture the waveform, you're just sort of looking at the input on the Wavesaver converted to digital, maybe back to analog again, then displayed something like that. I'm not 100% sure. We'll have to give this a test if this thing actually works. The Wavesaver's scope output frequency is a constant 400 kilohertz, and therefore the total output sweep time is always 10.24 milliseconds. And therefore, yeah, when you set to 1 millisecond per division, an oversweep of 96 data points exists, and 400 data points will occupy each scope division. So it's relatively high resolution, it sounds like. And yep, it says like how this works is it uses a DA converter, digital analog converter, to output the stored waveform to 0 to 8 volts. And I suppose it sounds like the input waveform, I haven't quite figured it out, but it might be 5 volts to minus 5 volts. And that would be the waveform that's going into the Wavesaver itself. They have a pinout for the parallel data output on the back. It's pretty simple. So it is just normal parallel data. And I guess there's some external sync trigger, stuff like that as well. I'm just wondering if it has like a test signal or something. Set up the oscilloscope as follows. Yep, all the usual stuff. Right, doesn't really say, oh, it says you can get a scrambled display on power up sometimes. This is normal since the memory of the Wavesaver has not been properly reset after power on. To reset the waveform, simply press or place the AC-DC ground switch to the ground position, and it will record the ground into the memory buffer. And kind of reading through the rest of this, talks about the outputs, the digital outputs a bit more. Oh, we have a little graph here, which I'm assuming is, yep, there we go. It's what you can print out using like a digital output, probably with that software there. And that's really it for the manual. And then let's see about the software. I have to try to archive this stuff. I doubt this stuff is archived anywhere. So it allows you to take, let's use this PC software to take your output from this device and then probably look at it. So runs on PCs or clones, MS-DOS 1.1 or 2.0. The computer should be equipped with 128K of RAM. Okay, a little bit more than it said on the other thing. It does use IBM CGA graphics, which was fine. That's what the first interface that came out for the PC was. And let's see, do we have screenshots and stuff? Well, it's pretty basic, but there it is. I think that's what the program looks like. And it looks like you can use BASIC if you want to actually pull the data in too. Anyways, okay, well, there's the manuals, and that's all the documentation. I'll look at the software in a little bit. Let's just see if the disk looks okay here. Yeah, this disk looks fine. Hopefully all these disks will be good and I can archive all of these on my grease weasel. All right, so here's the instrument again. So we have a trigger level control, offset, DC, AC, or ground. That's what I was talking about to do a reset. Someone's put little dots on here for, I guess, typical positions for everything, like there, right here for 2 volts plus or minus. Assume these are push buttons in and out. All of these are actually. Triggers, external, internal. Input is here. So if you're going to do an external trigger for the input, that would have to be something on the back. So external clock. So my assumption is that would be something over the digital port, because I don't think the external clock has anything to do with it. I thought in the manual it talked about there's external trigger inputs on this connector. This is the output trigger and the output signal that would go to your scope. I can hook these up to my bench scope and we can see what this thing can do. All right, so first thing I'm gonna do here is I'm gonna try to plug this in to see what happens. I'm gonna plug it into my little power strip here, which is currently off. The power switch is in the down position, so it's off. Okay, power switch is on. Here we go, let's see if this works. 3, 2, 1. Power lights are on. That's a good sign. Or this light's on and the trigger level light's on. So we'll just turn it off for now while I go grab some BNC cables to get that hooked up into my bench scope here. Okay, I have the output and the trigger connected to my virtual bench. All right, so we're gonna set this up. Trigger is external BNC. I forgot if it wanted rising or falling. I don't think it matters. We can fix that. It's amazing how absolutely slow you have to run this, this scope at. 1 millisecond per division, 2 volts per division for the voltage scale. And I'll put this down here because I know it happens to be 0 to 10 volts or something like that, I think is the range it's gonna output. It's not gonna go below that. And I have it set for external trigger. Let's turn this on, see what we get. Oh, you know what? I have this set for probe attenuation. There we go. So it's just stuck up at, what is it, 8 volts. I think this thing may not be working correctly. That are marked on here. My assumption is we should be seeing stuff change on the output. It's just stuck at 8 volts. It's set for DC, ground, AC. I don't think that's correct what we're getting there. Oh, wait, hold on. There we go. It was set for internal or external clock. I think. Wait, no, it was set for internal clock. It's very hard to tell which is in and out. Okay, in is external clock, out is internal clock. It's giving us a trigger, yeah, of around 400 kilohertz, which I think it said that's what it was going to do. Let's switch this to... It certainly looks a lot different than it did a second ago. By the way, I do have this actually connected up to the output on my virtual bench. It's like a 1 kilohertz test signal. So, yeah, this is acting weird. Auto trigger. Oh yeah, wait, there we go. That's probably our test signal right there. Oh, I think the controls are very scratchy. Let's just move it back and forth a bunch of times. Yeah, this position actually looks okay. This is 2 volts per division. The signal's actually like... I think now we're having trigger issues. Okay, so I really do think it is actually displaying correctly. So I think this little notch you see right here, this is actually like restarting the waveform display, because that's exactly where the trigger point is. So realistically, on a normal oscilloscope, the trigger point would be off the edge, and this is what we're looking at. Now, if I unplug the input here, I'll take it off the output of my virtual bench, it still stays there. Like I'm holding the probe here. Oh, well, it disappeared there, but it was there. Let's put the probe back on. All right, how do I get this to re-trigger? Okay, well, I've lost, oh, there we go. I don't know why that kind of disappeared, so I unplugged the probe again. So there's our probe. Now if I do manual trigger, oh, yep, it just takes a second. It's kind of slow, actually. I'm assuming it has to process the data before it outputs it, or something like that. So I'll reconnect it to the output, and there we go. Now we're not seeing anything. I'll push arm, trigger. Oh, yep, there we go. Okay, well, I mean, it's working. It's just so primitive compared to what we're used to. But if you had a normal analog scope, we would just be seeing this waveform all the time. Even if I, take the probe off like this, we'd still be seeing that waveform. So if you trigger appropriately, you can capture stuff and display it. I mean, it's all things we're so used to doing now by just pushing like the single shot button. But this is just constantly displaying this particular waveform. Now, one thing that's weird is like the DC offset seems a bit high, and I don't know why that's the case. Offset or center? Push it in for center. Okay, I'm gonna recapture this waveform. I gotta hook the ground probe up. Let's unplug that. See if I can get the waveform to go away. Okay, there, the waveform went away. So it's at 5.33 volts, which I think that is what it said would be the 0 volt point. Actually, it looks like it said that 4 volts would be the 0 point. So I don't know why it's up at 5.4. So there's like some kind of an offset or DC offset in here. But there is a kind of an offset control, but I don't know which one it is here. Well, we just have to kind of make the assumption that it's kind of drifted out of calibration. Can I recapture that waveform? Not sure these buttons are working super well. I have it set for manual trigger mode, and you figure pushing arm and trig should capture the waveform. Oh, I think we have just a bad connection on the BNC jack, to be honest. I'm going to put a little drop of deoxide in there. That actually might be what's causing part of the issue, is we just have a bad connection there. There we go. Just a tiny, tiny little bit in there. Either that or we just have some scratchy controls. All right, I'm going to try to speed up the time base. Time per point. Time per point. Did that actually speed it up? Yes, that does speed it up. So this is like increasing the time base. We're doing it on this, not on the oscilloscope, because the output of this thing is always the same. So we're looking at a 1 kilohertz output, by the way. I really think these controls are very scratchy, making everything kind of not respond very well. It seems to kind of be working though. It really, really does. I'm pretty amazed by that, to be honest. I'm pretty amazed. This thing is basically digitizing the signal, then it displays it on the output. That would display perfectly on an analog oscilloscope. I mean, how freaking cool is that? I mean, actually, you know what? We can turn on the AC coupling on this scope, which will bring it down. And then we can increase the resolution a little bit. So there we go. And I think I can change the volts per division. Let's put it at 0.5. Well, it didn't really change. Okay, I assume that's clipping there. This is 2 volts per division. Yeah. This control is scratchy. You see how it kind of like jumps around when I change it? It's getting better though. All right, so this thing has an arbitrary frequency generator on it. Let's plug this in and give that a try. How do I bring that up? Function generator, okay. Okay, 3 kilohertz. Turn this on. There it is. What are we generating here? Sine wave. Okay. Let's increase the amplitude. Right. I mean, it's working. Yeah, it's totally doing it. There it is. There's our sine wave. And we can increase the resolution or whatever, the time base, so we can see this a little more clearly. Yeah, there's a sine wave being captured. And we can recapture the waveform. Like there's triangle wave, square wave. The arbitrary generator, unfortunately, you need these files, and I don't have the original files for it, so all I can do is DC level, which is lame. So there's our sine wave. Let's see how high we can go. So we're at 3 kilohertz. I don't think this thing can go much faster than that. I think it said it can go up to 10 megahertz. First, we'll start with 1 megahertz. That's aliased really bad. Trying to go as fast as possible. 1 megahertz. It said it's good for 10 megahertz, but that's a stretch. It is losing amplitude pretty fast there. So I think it's not really, so I don't think it's really particularly good at anything high speed. Triangle wave, see how like curved off that is? I'm pretty darn amazed that this thing absolutely does work. I think, you know, with the appropriate cable sets, if you were trying to capture something on, you know, a computer or a circuit you were working on, so you could trigger off something like a chips-like line, maybe you could look at some other signal. I mean, with the right creative thinking, I think this could be pretty darn useful. And I have to think that whoever had this, or, you know, Dr. Larry Shore, was totally blown away by this thing back in the day. I think what we need to do is open this now and look inside. This one has a missing fastener, and someone glued the foot on. There's the underside. I love it. I love it. I love the construction on this thing. And I mean, it still works. So you really got to give them credit for that. Let's see if we can pop the top off. Hopefully see all the goodies, like the ICs and things in here. Oh, it all sort of fell apart on me. All right, there it is. Lots of logic ICs. There's a transformer. We have a voltage regulator, probably 7805. The caps are looking good. Front panel has an IC or two on there. Oh, a few things. Oh, a bunch of ICs actually, op amps and whatnot. And then let's see what's on this board, because this is where all the magic is clearly happening. Let's flip this around so all the electrons don't fall out. Epic Instruments, part number 10AD. All right, so that part, which is probably the analog to digital converter, it's very hard to read. I'm gonna try to get a better view of that. Okay, it looks like it's had the part number actually rubbed off on it, sanded off, just barely make it out, but I can't quite make it out. You can just see it ever so slightly there, but it has been physically abraded, so on purpose. We can assume that these are all SRAMs that are somehow amazingly all working perfectly. 8324 is the date code on all of those. I'm able to kind of turn up that these are SRAMs. Not a lot of info on them though, but we can make the assumption these are 4K by 1 SRAMs. And then a whole assortment of TTL logic and whatnot on here. Really nothing special. I wonder if that's like a DC offset output, or maybe that there. We have 2 different potentiometers and we have controls on the front, but this is probably for the front end digitization that's happening. And would have been my assumption that we have a digital to analog converter on here as well. It's probably that right there, DAC 08EN. It's interesting when you look at this stuff, like the case, it's all made in the US. Everything here is probably made in the US, or most of these chips were. Not necessarily all of them, but most of them would be. Kind of makes me wonder, because one of the feet here has the foot glued on, had someone been in here already and poked around or had to do some repairs or upgrades even. And when someone was in here, they lost one of the fasteners. So I had to get creative with a little bit of glue. Okay, no, I think the problem actually is the standoff is broken or something, because this one doesn't go in anymore. So I think I have to take this cover and rotate it around. Yeah, I can't really see that there's any kind of problem under here, but my assumption is whatever that fastener goes into down at the bottom, that is messed up or missing. All right, there it is, all back together. These plastic cases are kind of annoying to get back together, but you know what, to be honest, after all this time, it's still in good shape and it still seems to turn on and work as far as I'm aware. So yeah, very cool. Well, thank you, Gavin, for sending in this very interesting stuff. I got to open the ADC-1 again and take photos. I forgot to take any pictures of the inside of this. So that way, when the manuals and the discs get archived, if these discs work, let's keep your fingers crossed that they do, then at least I have some internal pictures to upload. And of course, all this stuff will go on archive.org. So hopefully there's a record that these things actually exist. If you were around back in the time when these things were used and you happen to have used either one of these, I would love to hear all about it down in the comments section, because it's fascinating to see early examples of home automation stuff that is so ubiquitous now. But I mean, this was the beginning of all of that. And I'm just kind of amazed by it, to be honest. And then the whole digital storage add-on for your analog scope, how freaking neat is that? And if you have any recollection of like when you first used a digital storage scope and in what context, was like at work because it cost $50,000 and they paid for it, or you had one at home, I mean, I'd love to hear about that stuff too. This is all fascinating to me. The very first oscilloscope I ever had was just an analog, cheap, like 20 megahertz or 40 megahertz thing or whatever it was, and I got it sometime in the 2000s. It was a surplus device and it worked for what I needed to use it for, just to look at waveforms when I was fooling around with Arduino stuff, basically. But as for actually doing real troubleshooting work with it, totally you can do it. But the fact that digital storage scopes exist now and are so ubiquitous and so cheap, stuff like this that just cost like $80, that's frankly amazing, because I think this crappy scope, as junky as this really is, it's far more capable than even the most expensive thing from the old days. And it's just so ubiquitous and so inexpensive and battery powered and, you know, on and on and on. So we're in a different world now than we were back in the 80s and even in the 90s and even in early 2000s, where digital storage scopes were very expensive. I guess my first digital storage scope that I bought was a Rigol, I don't even remember the model number of it, 1054, or is that the one I have now? I think that's the one I have now, 11 something or other, the one that Dave Jones talked about. It was very capable, and it was only like $400 if I recall, which was revolutionarily cheap for back then, because everything else was like Tektronix and stuff and very expensive. So things changed very quickly, very recently, and that's where all my experience comes from now, is troubleshooting with my modern tools. So having to work with this older stuff, especially this what's it called again? Waveformer? Wavesaver. Wavesaver. Having to work with a Wavesaver, I think, could be a real boon if you could make it work the way you need it to work. And obviously, Dr. Larry Shore, who used this complicated harness with it, obviously got good use out of it. And who knows how many how many students learned from him and became electrical engineers, and maybe there's some famous ones in there. So anyhow, thanks very much for watching. Thank you, Gavin, for sending this stuff in. If you like this video, thumbs up. If you didn't know what to do, thanks to my supporters, all the usual YouTube junk, and that's going to be that. So stay healthy, stay safe. I'll see you next time. Bye.